Welcome to the first video in our series on UV-Vis Spectroscopy, Ultraviolet Visible Light Spectroscopy. In this first video, we will be looking at the instrument itself and how it actually works. We will be looking at a very basic version of a UV-Vis spectrometer. This particular instrument is single beam and slightly less complicated than the instrument that we will be using in the laboratory. In the course of this video, there are three objectives that we hope to achieve. First, the student should be able to identify most of the important components of the UV-Vis spectrometer. Second, they should be able to track the light path throughout the spectrometer from the lamp to the detector. And then finally, the student should also be able to explain how the wavelength selection portion of this instrument works. Right now, you are looking at an image of a UV-Vis spectrometer that we keep in our laboratory. This particular spectrometer is not actively used, but rather used as a demonstration piece. It's an older model, and it's a very simple model. However, it will serve the purpose of demonstrating how the light moves around the instrument and what some of the principal components of this instrument are. One of the first features that you will notice about this instrument is the presence of a door on the front of it. This door is the door to the sample compartment. By opening this door, you can gain access to where the cuvettes are actually placed in the instrument. You may notice that the entire inside of the sample compartment is painted black. The reason for this is to minimize any stray light that may reach the detector. Please note that this door needs to be shut anytime the instrument is in use. The image that you are looking at right now is a close-up of the sample compartment. You will see that there is a plastic holder where we place the sample cell. Notice that there is only one sample holder. That means that the instrument can only look at one thing at a time. You will also notice that there is a port or a window where light can enter from the light source, and a port that leads to the detector, where the amount of light passing through the sample can be detected. Looking at the top of the instrument, you'll notice that there's a panel that can be accessed by simply unscrewing the knurled nuts that are on top. This panel provides access to the UV and visible light lamps that are needed for this instrument. These are considered consumables as they do burn out just like light bulbs do in your home. As expected, opening the panel reveals the two lamps that are utilized in this instrument. You can see that there are clearly two, one that has several wires going to it and one that has only a couple wires going to it. Both of these housings can be removed by unscrewing the knurled screws that are at the top of this holder. Removing the lamps from their housing reveals the two individual lamps that are used for this instrument. On the left-hand side is the UV lamp. This is a deuterium-based lamp, while the one on the right-hand side is a visible light lamp. Altogether not too different from a flashlight light bulb. As you can imagine, the UV lamp is considerably more expensive than the visible light lamp. So make sure that you turn off the instrument at any time it's not being used. It should also be noted that great care should be taken when handling these lamps. They should not be held with bare hands. All measures should be taken to avoid contact with the envelope itself for each one of the lamps. Now this is what the instrument looks like with the outer case removed. Please note the positions of some of the key components that we've already looked at. Make sure that you can identify where the lamps are and where the sample compartment is. As we proceed here, we will look at the wavelength selection or the monochromator, as well as the detector system for this instrument. Now by zooming into the top left-hand portion of the screen, you'll see that we have our light source, our deuterium lamp, as well as our visible light lamp. That light is focused through a system of mirrors, through a slit, and that slit sends the light through to the wavelength selector, in this case a diffraction grating. And that diffraction grating spreads out the different wavelengths of light spatially, such that only one, in this case yellow, can make its way through the next slit. Now, upon going through that slit, the light then makes its way through a colored filter and then bounces off 2 more mirrors before being sent to the sample compartment. And once it's in the sample compartment, it can go through the sample and then ultimately to the detector. Next, I would like to show you some of the components of this instrument up close. Right now, you are looking at the diffraction grating. Please note that it is concave and that it is etched with a series of lines that are very close together. You can almost see the rainbow effect that's being created within this image right here. This is an image of the first slit in the wavelength selector for this instrument. Please notice that the slit is so small that you can barely detect it by the naked eye, and it's not exactly a high-tech piece of equipment here. You can see that most of the slit's construction is actually made up of duct tape or some other type of electrical tape. Clearly, this piece of equipment is not equipped with a slit width that is changeable, unless you are willing to open up the instrument and adjust it by hand each time. Thus far, the instrument's detector has been essentially invisible to us. As you can see, on the right-hand side of the sample compartment, there is a ribbon cable that is attached to a little metal piece. By disconnecting that metal piece with a Phillips screwdriver, you can see the actual sensor that is used as the detector. This particular detector simply measures the intensity of light that is hitting it. It does not know anything about the wavelength of the light, just simply the intensity. As stated before, this instrument that we're looking at is a single beam spectrometer. That means that at any given time we can only look at one sample. That means that during the course of an experiment we need to replace the sample with a blank back and forth every time we change a wavelength. This can make measuring this wavelength spectrum, or the UV-Vis spectrum of a sample, very difficult and very time consuming. It would be much more efficient if we could measure the blank and the sample simultaneously. And this is an issue that is resolved by the double beam instrument. There are 2 different types of double beam instrument. There is the double beam in time instrument and the double beam in space. The next video will look at the differences between the 2, as well as introduce the instrument that we will be using in the laboratory. Thank you for taking the time to watch this video, and please make sure that you get to the laboratory and practice on this instrument as much as possible.